So solubility equilibrium. This is going to be our last part of equilibrium. We've done KEQ, just general equilibrium. We've done KC, equilibrium with concentration. We've done KP, equilibrium with pressure, with gases. We've done KA, KB, equilibrium of acids, bases, and KW, the equilibrium of water. This is our very last one. This is going to be KSP, equilibrium solubility product constant. Before we go into that, let's go over the difference between ionic and molecular compounds and the ionic and molecular solutions. So the first thing we're going to do is look at how to tell whether a solution is an ionic or a molecular solution, and whether or not these ionic or molecular solutions conduct electrical currents. So in this unit, we're interested in the solubility of ionic substances, not molecular covalent substances. However, we need to be able to distinguish the ions before we can analyze their solubility. So looking back at our old school Chem 1 periodic table, we need to be able to identify where our metals are, our nonmetals, and all the charges on top. So rules for ionic and molecular solutions. 1. Compounds that are made of a metal, something from the left side of the staircase, and a nonmetal, something from the right side of the staircase, form ionic solutions. Here are a couple of examples. NaCl forms the ionic solution, where we have NaCl dissociating into Na and Cl-. Notice we have a solid dissociating into two ions. Ions must always be aqueous. Okay? Aqueous is a solution, so it's keeping these ions separate in a solution. AlCl3 also forms an ionic solution. We have our solid separating into its ions, aluminum 3 plus 3 Cl-. Even in net ionics, they must be balanced. We need to have the correct number of ions that are coming out of this solution. Both of these substances are made up of a metal and a nonmetal. When they are dissolved in water, they break up into free ions. Okay, so these ions separate and form different amounts inside this solution. Compounds containing polyatomic ions form ionic solutions. Remember, if you can find a polyatomic ion on the table of common ions, although you can't, I originally wrote these notes for my pre-AP class. So whenever I adapted them to you, I missed this little line. You don't get a table of common ions, you get your brain. You need to have the polyatomic ions memorized, especially by this point. Okay, polyatomic ions are very crucial to some very basic points and some beginner points. So some examples of the most common ones are going to be carbonate and nitrate. Carbonate is used pretty often because calcium carbonate has a molar mass of 100, so they love that one. It's really easy to do calculations with. And also nitrate because it's the always soluble polyatomic ion. So here's another example of a compound which forms an ionic solution. If we have KMnO4, we're separating into our potassium ions and our permanganate ions. Covalent compounds are made up of a nonmetal and a nonmetal, two of them, generally form molecular solutions. These include compounds in which both elements are found on the right side of the staircase. An example is sulfur dichloride. So both the S and the Cl are from the right side of the staircase. Another example would be iodine. Remember, iodine is one of our diatomics. When it dissolves in water, it does not break apart into ions. It simply stays as neutral molecules and disperses itself in the water. The equation for it dissolving in water would be, I have my diatomic molecule as a solid becoming diatomic aqueous. Notice there are no ions in the products, just I2 molecules. So what causes conductivity? If a liquid conducts an electrical current, it means that the liquid must have ions in it. The only exception to this is liquid mercury, which is a metal. Okay? All of those metals do conduct electricity already, so it doesn't actually need to be in an ionic form that liquid mercury will conduct electricity. But all other things, all other liquids that conduct electricity have ions in them, meaning they're aqueous solutions. So even though a solid ionic compound is made up of ions, all those ions are stuck together and immobile. So electrons are not transferring, and therefore an electrical current is not transferring. And so solid ionic compounds do not conduct electricity in the solid form. So when they are dissolved in water, the ions are removed from the solid and move independently anywhere in the solution. So we start out with a solid where its ions are put into the water and they float off, being attracted to the polarity of the water. So the positive and minus ions are now free to move around. The positive ions are attracted to a negative electrode. The negative ions are attracted to a positive electrode where they transfer electrons, and therefore ionic solutions conduct a current. Remember, pure water does not conduct any electricity. You need an ion to actually transfer electrons and therefore actually create a current. While water molecules are polar, while they do have a slightly positive and a slightly negative end, that slightly positive and negative end doesn't actually transfer any electrons, so there is no electricity there. So for a molecular solid, like I2, if I had it in a solid, it'd be in a rigid structure, and then I had it dissolving. Notice my interaction here. It's just iodine and water, iodine and water. They're all dispersed, so it has dissolved, but it's not actually being able to create a current. There's still no positive and negative, no ability to transfer electrons. So in summary, you can tell whether a solid is going to form an ionic or molecular solution based off what kind of compound it has. Compounds of a metal or a nonmetal will form ionic solutions. Compounds containing a polyatomic ion will form ionic solutions. Compounds containing only nonmetals will form molecular solutions. Organic compounds, those ending in anything besides COOH, so any organic compound, any compound of C's and H's, large or small, form molecular solutions. The only exception to this organic compound rule is an organic acid. So that's one of those that end in COOH. Okay, one of these that end in COOH form a partially ionic solution, which you should be able to identify, because if something is called an acid, it must be donating a hydrogen ion, meaning it's donating an ion, meaning it has ions, and all ions conduct electricity. So both numbers 4 and 5 are probably something you won't see again, but it is something I want to include here. Okay? All your organic compounds are molecular except for your organic acids, and that word acid should be your clue that it actually will form a partially ionic solution. So solubility and solubility equilibrium. What is meant by the term solubility? Well, what conditions are necessary to form a saturated solution? What is happening at equilibrium in a saturated aqueous solution? And how to write the net ionic equation, which represents a saturated solution. So try to imagine what happens to the ions of a soluble solid ionic compound as soon as you put it into water. The following diagram should help you. Notice this time I did not include the water molecules around the ions. We know they're there, but it's easier to look at them as just the negative and the positive ions. When the solid is first put in the water, the rate of the dissolving is high when there's lots of room for the solution for the ions. So it dissolves and it floats away. Dissolves and it floats away. So the rate of the precipitation is 0 at the beginning. Remember, precipitation is the formation of a solid. So you put a solid into the solution and the ions start floating away. At first, only the forward reaction is taking place. My ionic solid is becoming an aqueous solution. However, this situation does not continue for very long. As the dissolving continues, more and more ions are going to be in the solution. Therefore, the chances that one of those ions will come back and collide with that crystal and stick to it gets greater and greater. If a negative ion collides with the crystal where a positive ion is, it's still attracted to that crystal, so now it actually attaches back onto the solid and therefore precipitates or crystallizes. So while at first all we did have was dissolving, we begin to have the reverse. So we have our reverse rate, where this ion actually went and bounced off something and came back, and now it's attracted to this positive crystal, this positive part of the crystal, and so it reattaches. So now we have a reverse reaction. If we have a forward and a reverse reaction, and once these two reactions have equal rate, we have equilibrium. Forward and reverse reaction, equal rate, and constant concentration. So as more free ions are found in the solution, the rate of precipitation will continue to increase. Also, because the solution is getting full of ions, it's getting saturated, the rate of dissolving will decrease. Sooner or later, the two rates will be equal, and therefore we have solubility equilibrium. Solubility equilibrium exists when the rate of dissolving equals the rate of precipitation. So the solution that forms when some solid is still present and where solubility equilibrium exists is called a saturated solution. So we originally learned unsaturated, saturated, and supersaturated. Unsaturated, there is some crystal, there's some solid in there, it's not fully dissolved. Okay. Saturated solution, we've dissolved as much as we possibly can. Supersaturated, we've dissolved more than we really should. We've held it in this very unstable state. So my saturated solution is a solution in which there exists a dissolved substance in equilibrium with its undissolved substance. Okay, we've dissolved the maximum amount of solid possible. And so we have this dissolving and crystallization, equal rate in both directions. So this equilibrium can be described by an equation with a double arrow. If we say equilibrium, it must be a double arrow. So a real example might be calcium carbonate solid is in equilibrium with calcium and carbonate ions. The term that describes how much solid dissolves at a certain temperature is called the solubility, like the ability to dissolve, or to become the solute. Because the solute is the thing that is dissolved, so solubility, the ability to become the solute. If something is soluble, it is able to be the solute. Another way of saying this is that the solubility is the amount that has dissolved at a given temperature. Specifically at a given temperature, because remember, the only thing that can change equilibrium, the K, is temperature. So it has to be at a specific temperature. This is the certain solubility. So remember that once equilibrium is established, dissolving will continue. Anytime you reach equilibrium, the forward and the reverse reaction continue. So dissolving will continue, but so will the precipitation at the same rate. So the concentration of the solution will stay constant as long as the equilibrium is maintained. This concentration is called the equilibrium concentration. So a definition of solubility based off equilibrium is that solubility is the equilibrium concentration of a substance in a solution at a given temperature. So you're looking for the E on the ice table. Net ionic equations for solubility equilibrium. As we mentioned earlier, when a dissolving substance is at equilibrium, the rate of the dissolving is going to equal the rate of the precipitation. We can show that this is at equilibrium by writing our double arrow. So we either do this one on top of that one. Sometimes you'll also see it written like this. Chemists have chosen to show that the solid is on the left being dissolved into its ions on the right. This isn't necessarily how it would have to be done, but this is how it's written traditionally, so you should do it the same. So you always put your solid in equilibrium with its ions. So for magnesium sulfate, we would write its dissolving equation as my solid on the left, dissolving into its ions of magnesium and sulfate. Make sure your ions always have their charges. If they don't have their charge, that's incorrect. SO4 and SO4 2- are two entirely different things. Also, anytime you draw ions, they're always aqueous. Things only exist as ions inside a solution. So, because we're using our equilibrium arrows, this does mean that we are becoming our ions and are precipitating our solid at the same rate. Equilibrium, equal rate, constant concentration. So since a saturated solution exists at equilibrium, then we can also refer to this equation as to showing what is going on inside a saturated solution of MgSO4, or the equation describing the equilibrium present in saturated MgSO4. Either one would be the correct way of explaining this. So this is a saturated solution because we're at the equilibrium, so we either use this as our equilibrium expression or our saturation expression. The major use of solubility with a lab would be using solubility to separate ions from a solution. So if we're going to be separating ions from a solution, we're going to be creating a precipitate and using filtration. So if we were using filtration to separate our precipitate, we use our funnel, we use our filter paper, and the precipitate will stick to the filter paper. Ions will always go through filter paper. Ions are part of the solution. So all of your ions will pass through, just like salt water passes through a funnel with filter paper without leaving any salt behind. Unless that salt water is a supersaturated solution, something where there is going to be precipitate coming out of it. So only precipitate will be left behind, the rest of the ions will come through. So the precipitate will be trapped in the filter paper, and any soluble substances will be dissolved in water and go through the filter paper. If there are more ions to precipitate, substances could be added to the filtrate and again precipitate. So if I was to make one precipitate and filter it out, and then I still had ions down here, let's say there's still some lead ions in the solution down here, I could go and create another precipitate and filter that out. So I could be separating the ions one at a time using this system of precipitation. Now for our final K calculations. This time we're going to have Ksp. SP would be solubility product. So K is the same as always, our equilibrium, capital K, and then solubility product calculations. So we're going to learn what is a Ksp, how to write the expression, same as always, how to calculate solubility, which is just another way of saying the concentration used, and how to calculate the value of Ksp. I hope all of this looks very familiar to what we've been doing so far. So first, what is Ksp? Ksp is really nothing new. It's simply an equilibrium constant, just like Keq or all the other Ks, but this time it's specifically for an ionic substance dissolving in water. So for example, if we have calcium carbonate, a solid, when it dissolves in water, it forms calcium ions and carbonate ions. So to write the equilibrium net ionic equation, we have our solid using equilibrium arrows with its ions. Then to write my Keq, it's always products over reactants. So I have my products to the power of their coefficients, each of which are 1, but my reactant is a solid. And remember, calcium carbonate is not included because we never include pure solids, pure liquids. All we ever include are aqueous solutions and gases. So remember that the solubility was defined as the equilibrium concentration of a substance in water. But when ionic compounds dissolve in water, you're always going to get at least 2 ions. So in this case, calcium and carbonate. So if we plug in our concentrations into our Keq expression, that would give us a constant for the solubility of these ions. In other words, KEQ can be thought of as the product of the solubility of the two ions. So for ionic compounds dissolving in water, the KEQ is given the special name solubility product constant, or KSP. For writing a KSP expression, we're going to always use our net ionic equation. We don't care about spectator ions, they don't play a role in anything. So there's nothing new to this. We always leave out the solid, just like we left out the pure liquid water and acids and bases. And we're going to change our coefficients in the balanced equation to our exponents in the KSP. So like always, K is always equal to our concentration of our products over the concentration of the reactants, each of which to the power of their coefficients. So for lead 2 chloride, we have PbCl2. It's always solid first, equilibrium arrows, then the ions, separate it into its ions and balance it, 1 lead, 2 chlorides. So the KSP expression would be KSP of my products over my reactants. This is a solid, so we don't write it. So Cl to the 2 power for the 2 coefficient, and then Pb2 plus. Notice our 2 does not go in front, it is an exponent. So for silver sulfate, same concept. We write out the compound correctly. You would have to write it correctly with the correct charges, otherwise you'll mess up your balancing. Solid, equilibrium arrows, ions, coefficients of 2 and 1. Write out the expression KSP, silver to the 2 power, sulfate. To keep these simple, remember the following 2 rules. Leave out the solid and change coefficients in the balanced equation to exponents, just like always. So for calculating solubility given KSP, so this is our first type. We're going to calculate the solubility in moles per liter, in other words, molarity. So we're going to be given the value of KSP to start with. We're going to be calculating for a concentration. Okay, same kind of equilibrium calculations we've been doing. We only consider the KSP and the solubility of substances which have low solubility on the solubility table. Now in AP, we no longer have to memorize our solubility table, exactly which things are and are not soluble. Instead, we memorize our 1 solubility rule, and based off of that 1 solubility rule, if it does not fall under our 1 solubility rule, if it does not possess a sodium, a nitrate, a ammonium, or a potassium, then we consider it to be of low solubility. These are also called slightly soluble salts. So for these calculations, we can define our molar solubility, so this is what it's asking for, our molar solubility, as the moles of the substance which will dissolve in 1 liter of solution to form a saturated solution. In other words, this is how much in molarity does the salt dissolve. That would be its solubility. So if I was given the KSP for silver chloride, AgCl, I could write the net ionic equation, solid, AgCl, in equilibrium with its ions, Ag plus and Cl minus, solid, aqueous, aqueous. Make sure it's balanced, 1, 1, 1, 1. The number of moles of AgCl which will dissolve in 1 liter, meaning the molarity change for AgCl, is going to be defined as S, S being its solubility. So notice on the equation I put a minus S above the AgCl. This is because when you dissolve the AgCl in water, the amount of solid will go down by S, however much, because that much is what dissolves. Our S is really the same thing as our concentration change in our ice table. So once again, it's nothing new. We're just going to define it as S. You could still just put the C and just know to answer when it asks for solubility. That is your change. How much of this was actually dissolved? That would be your solubility. So if we look at our mole ratios, we can see that the Ag is in a 1-to-1 ratio with the Cl and the AgCl. So if this is going down by S, this would go up by S. Same thing for the chlorine. If this goes down by S, this goes up by S. Remember, we're looking at it just as if we were doing an ice table. So we have a minus S, and plus S, where S, once again, is the moles per liter of AgCl which will dissolve. It would be the same thing as our C in our ice table. So our Ksp expression for this equation would be our products, Ag plus and Cl minus. They both have a 1 coefficient. We do not include the solid in our expression. We plug in our equilibrium concentrations, which for this case would be our S's. These would come from our ice table if we made it that way. So we have S and S. Plug these in, and I get Ksp equals S times S, or Ksp equals S squared. So if we were to solve for S, we were given this Ksp at the very beginning of this problem. So our Ksp was 1.8 times 10 to the negative 2, 10. So then, in order to square root this, S is the square root of 1.8 times 10 to the negative 10, which gives me 1.34164 times 10 to the negative 5th molarity. I will round this off for sig figs for my final answer. I'll give you a second to copy this down. So since we defined S as the molar solubility, when we solved for S, we did in fact solve for the molar solubility. So this would be moles per liter of AgCl which dissolved. Even though AgCl isn't included in our Ksp expression, it's directly proportional to our answer because our S was the molar solubility. So if I round my answer of 1.34164 times 10 to the negative 5th to sig figs, start out with 2 sig figs from the 1.8 times 10 to the negative 10, which was my Ksp. So my answer comes out 1.3 times 10 to the negative 5th. Now, it looks awful tempting at this point to just say that molar solubility is the square root of the Ksp. But that only works in this case because we happen to have a 1-to-1-to-1 ratio. So instead, you need to make sure you follow these steps. 1. Write the net ionic equilibrium expression. 2. Use the Kxp expression. And 3. Use the concentrations plugged into the Ksp expression to solve for S. Do not take shortcuts. They can lead to trouble in this next. So this time we can actually calculate the Ksp given the solubility, back and forth. In the first example, we will do is to calculate the Ksp of a substance given its solubility. In this type of problem, we don't use the S's. The molar solubility is known, so we just need to use the concentrations of each ion. We can record them on the top of the equation if you don't want to have to write out an ice table. Next, we write out the expression for Ksp, plug in the concentrations to obtain the value of Ksp. So, for the solubility of silver chromate, solubility is 1.31 times 10 to the negative 4th molarity. Calculate the value of Ksp. First, always write out my equilibrium expression. Make sure it's balanced. So 1 to 2 to 1. The solubility given was 1.31 times 10 to the negative 4th. So we write that on top of the AgCrO4. I usually write it as a negative because that's what's going to be going down. That's what is dissolving. So I'll write it on top of my equation here. So using my mole ratios, I have a 2 to 1 of silver to silver chromate. So my change here would be 2.62 times 10 to the negative 4th. Once again, you could be doing this as an ice table. I'm trying to find a way to shorten it because most of you are trying to shorten it yourself. So if you're good with the ice table, same thing. Just put this down for your C. If you're trying to fix things by going quicker, at least do these steps where you're writing the numbers on top, so you at least have one row of shown work. So for CrO4, it will go up by 1.31 times 10 to the negative fourth because it's a 1-to-1 ratio. So once our solution is saturated, once the solubility has occurred, the amount of this that's going to dissolve has dissolved, we end up with concentrations of 2.62 times 10 to the negative fourth moles per liter for silver, and we have 1.31 times 10 to the negative fourth moles per liter for chromate. Remember, we have to use those mole ratios. I see that as a large mistake whenever we're doing the ice tables. So the Ksp expression comes out to silver squared chromate, using the coefficients as our powers. We plug in our numbers, and we get Ksp equals 2.62 times 10 to the negative fourth squared times 1.31 times 10 to the negative fourth, and that comes out to 8.99 times 10 to the negative 12th, using our original 3 significance digits given in the solubility. So we know how to calculate solubility for one substance by itself. Now how do we apply that for precipitate? In order for us to have a precipitate, we need to be mixing two different solutions, because we're combining ions that no longer stay in the solution. So how are we going to tell how a precipitate forms, and how to tell if it will form when a given mass of solid is added? So how do we predict a precipitate when two solutions are mixed? Well, first, our solubility rule tells us when a precipitate will form, right? So far we've learned that if it contains sodium, potassium, nitrate, or ammonium, it will never form a precipitate. And that's always true. But saying that all others will form a precipitate is not true. All that says is that all those other compounds with all the other ions possible have a solubility of greater than 0.1 moles per liter. So at some point in some situations they will form a precipitate. It'll be up to us to find out, is this one of those situations? So for example, based on the solubility rules, a precipitate will form when calcium ions and sulfate ions mix, because neither one of those are in our one solubility rule. However, if we mix calcium ions and sulfate ions in low concentrations, we might not see a precipitate. We would have to actually calculate to see what would occur there. The quantity which determines the concentrations of ions allowed before a precipitate will form, that's coming from our Ksp. So just like our K is always telling us how much products versus reactant, same concept here. Our Ksp can tell us how much of the solid versus the ions and whether or not that results in a precipitate. So let's look through an example using calcium carbonate. So if I have a Ksp for calcium carbonate, I write my Ksp expression. They each have a 1-to-1 ratio. If I needed to write out the equation, so calcium carbonate, equilibrium arrow, calcium ion plus carbonate ion. So I have a 1-to-1 ratio here. This means that in a saturated solution, which is just on the verge of precipitation. Remember, a saturated solution means it has dissolved all possible solid possible. So we're on the verge of precipitation. This is my equation. 5.0 times 10 to the negative 9 is equal to these two concentrations. Which means that 5.0 times 10 to the negative 9 is the most the product of the concentrations can be in order to not have a precipitate. As soon as one of these two goes past the point at which they're equal to 5.0 times 10 to the negative 9th, we are now past the equilibrium, we're now past the saturation point, and whatever exceeds that point of saturation, that's a precipitate. So if we look here, that looks like we're going to be able to calculate and compare. Just like how we compared Q versus K to see if we are at equilibrium, we can do the same thing here. Because we said if we are at equilibrium, we are saturated. If you're saturated, there is no precipitate. Once we have passed that point, once we have exceeded our Ksp, now we are forming a precipitate because we now have too many ions to keep this equilibrium of saturation. So when mixing two ions, they must have come from two different sources. There is no such thing as a solution of pure calcium ions. Ions are formed by separating them from another substance. So in other words, when we mix one solution that contains calcium and another solution that contains carbonate, this is when a precipitate can form, depending on the amount of each. Now there's nothing that says we're using equal amounts of calcium and carbonate ions. All we know is that if calcium times carbonate becomes greater than 5.0 times 10 to the negative ninth, a precipitate will form based off of our Ksp expression. So if we're given a problem that gives us these concentrations of calcium and carbonate to be 2.3 times 10 to the negative fourth and 8.8 times 10 to the negative 2, the Ksp for calcium carbonate, once again, is 5.0 times 10 to the negative ninth. Will a precipitate form? All we do for this is we solve for a trial ion product, TIP, or really a trial Ksp, also known as Q. So if we substitute the values for the concentration of calcium and the concentration of carbonate into our Ksp expression, we have our Ksp, we plug in our trial concentrations, and our trial Ksp comes out to 2.024 times 10 to the negative fifth. So now we need to compare our trial Ksp to the given Ksp. So our trial Ksp to our real Ksp. Since 10 to the negative fifth is greater than 10 to the negative ninth, my trial Ksp is greater than my Ksp. Now be careful that you're paying attention to these exponents. Often people will look at the 2.024 and the 5 and say, well, this is smaller. Times 10 to the negative fifth versus times 10 to the negative ninth is a huge difference. So there's a large difference in the solubility here. So now, since the Ksp told us the maximum amount of product that could be made without precipitation, we now know that a precipitate will form. So to summarize, when my trial Ksp is greater than my Ksp, a precipitate will form. When my trial Ksp is less than my Ksp, a precipitate will not form. Make sure you understand this concept, and the rest of this unit is very easy. So when we mix two solutions, a couple things happen. First, by mixing two solutions, we're really mixing 4 different ions. So as soon as we're pouring them together, 4 different ions begin interacting. Some of these ions might form a compound with low solubility, meaning something that will precipitate if given a high enough concentration of the ions. So both solutions will also become diluted because you're adding 2 volume amounts together. So the volume of the mixture is the sum of the volumes of the 2 separate solutions. So the only thing we're really adding into our calculations here is we need to consider our new volume and its effect on molarity. So let's look at how this works out. If I have 50 milliliters of 0.0035 molar calcium nitrate, and I mix that with 150 milliliters of 2.0 times 10 to the negative fifth molar sodium carbonate, will a precipitate form? Well, first, let's think about what 4 ions are going into the mixture. We have calcium, nitrate, sodium, and carbonate. So these are my 4 different ions possible in the solution. I start with 2 beakers that I'm pouring in, one of calcium nitrate, one of sodium carbonate. If I look at all ions possible, you should immediately recognize the spectators, the things that will do nothing. You only have 4 of them that you're for sure every time do nothing. So if you look at the rest of it, our possible results would be calcium and carbonate could combine. We need to know if this will actually form a precipitate. So this isn't just going off the logic that, oh, well, these 2 are soluble, so these 2 must form a precipitate. At some point, these do. They're considered of low solubility. What we need to know is, do these concentrations affect whether or not a precipitate will be formed. Is this enough calcium and is this enough carbonate that when combined, a precipitate will form? So we know that the Na and the NO3 are always soluble. That's how we got rid of the Na and the NO3. And we know that that will not form a precipitate. The calcium and the carbonate might form a precipitate based off if their concentrations are high enough. So let's write our net ionic equation for the only possible precipitation reaction. Remember I told you that for all equilibrium concentrations and all equilibrium expressions, they always need to be in their net ionic form. We got rid of the spectators of sodium and nitrate. Now, although when we mix the two solutions, we're considering calcium carbonate to really be a product of the two mixing, we aren't writing it as a product side because remember, the standard is to put whatever solid you're testing at equilibrium with its ions. So we assumed that calcium carbonate solid could be formed, and now we're comparing the ions that were given to see if this solid is actually going to be formed in this equilibrium system. We write our Ksp expression based off our correctly written net ionic. So we have our products to the power of their coefficients over the reactant, but it's a solid. So our Ksp for calcium carbonate is 5.0 times 10 to the negative 9th. That was given to us. And based off of this information, we know that the concentrations of calcium times carbonate cannot be greater than this 5.0 times 10 to the negative 9. Because if they are at the moment of mixing, then any of these extra calcium and carbonate ions are going to precipitate out as calcium carbonate. So if the product of calcium and carbonate is less than 5.0 times 10 to the negative 9th, then when they mix, there's not enough ions to surpass this equilibrium concentration and make precipitate. So we won't be past our saturation point until we've exceeded this Ksp value. So precipitate will not form unless this times this is greater than 5.0 times 10 to the negative 9. So in order to test these concentrations at the moment they are mixed, we're really testing a trial Ksp. So the original concentration of calcium in the beaker was 0.0035 molar, but when we mix the two, the volumes changed. So I need to use my dilution equation. Since 50 milliliters of the calcium nitrate solution is being mixed with 150 milliliters of the other solution, my total final volume, what gets plugged in there, would be 200 milliliters. So to find the volume or the concentration of calcium in the end, my molarity 2, we plug in, M2 is going to equal my original molarity times my original volume divided by my final volume. When I plug all this in and solve, I get 8.75 times 10 to the negative 4th molarity. So right after we mix, the concentration of calcium changes because its concentration is moles per liter, but liters changed. Moles didn't. So my molarity goes from being original 0.0035 all the way to 8.75 times 10 to the negative 4th. So this is my starting concentration of mixing for calcium. This is the number I will be plugging into the Ksp expression. The original concentration for the carbonate was 2.0 times 10 to the negative 5th. However, its concentration also changed when we mixed the two to our final volume of 200 milliliters. So to find this, once again, we use our dilution equation. We're solving for our final molarity of CO3 upon mixing. So we have our initial molarity times my initial volume divided by my final volume. And I get a final molarity of 1.5 times 10 to the negative 5th. So it was initially 2.0 times 10 to the negative 5th. Now it is 1.5 times 10 to the negative 5th. This is my concentration upon mixing. This is what I will be plugging into the trial Ksp to compare for my Ksp. So now that we have our calcium concentration and our carbonate concentration upon mixing, we add both of these into our trial Ksp. We solve. We get 1.3 times 10 to the negative 8. So if we look way back at the beginning of the problem, when it gave us our KSP, we get our real KSP was 5.0 times 10 to the negative 9th. Once again, look at those exponents. 1.3 times 10 to the negative 8 is greater than 5.0 times 10 to the negative 9. Therefore, trial KSP is greater than our KSP. So yes, a precipitate will form. That's all we need to do is be able to solve for a trial KSP, compare it to the original KSP. If it's greater, a precipitate always forms. So what if we add a solid to a solution instead of mixing two solutions? So let's do an example. Will a precipitate form if 2.6 grams of potassium carbonate is added to 200 milliliters of 2.0 times 10 to the negative 3 molarity magnesium nitrate? First, we check to see what ions we have, which ones will possibly combine to form a precipitate. Get rid of any of those soluble ions. Potassium never does anything, nitrate never does anything. So our two possible products are potassium nitrate, which won't do anything, and magnesium carbonate. So potassium nitrate will not form a precipitate. The only possible precipitate is magnesium carbonate. It must have low solubility since it doesn't have any of the ions that are always soluble. So just like we did before, we need to compare our trial KSP and compare it to the real KSP to figure out if a precipitate will form. To do this, we need to find the concentration of magnesium and carbonate immediately upon mixing. Well, the initial concentration of magnesium nitrate was 2.0 times 10 to the negative third in 200 milliliters. So that already is our concentration of magnesium nitrate. Now, why do we not have to change for dilution? Because here's an important point. Adding a small amount of solid to a large volume will not significantly affect the total volume or the initial concentration of the solution until a reaction occurs. If a reaction occurs and pulls out some of the solution, it may eventually change the molarity. But by adding just a small amount of solid to a beaker, we're not changing the volume enough to really merit changing our molarity. So we get to keep this original molarity of magnesium nitrate, and we can use this volume we had to use our grams to moles to find the molarity of the solid we added. So 2.6 grams of solid potassium carbonate is only really about a spoonful. So we can use that 200 milliliter volume and not worry about any change. So we can also assume that the magnesium, which is equal to the magnesium nitrate, because it's one of these in each of the compounds, does not change. So the magnesium concentration upon mixing is the original concentration, 2.0 times 10 to the negative third. This is the same as it was before mixing because there was no liquid added, so my molarity is not significantly changed. So the magnesium after mixing is 2.0 times 10 to the negative third. What we need to find is the carbonate. Immediately upon mixing, because that's what we're plugging into our trial KSP. So we can put these into our KSP expression. Using the 200 milliliters of magnesium nitrate as our volume, we change our grams to moles. For our potassium carbonate, so we had 2.6 grams of it, use our molar mass, and that gives us 0.0188 moles of the potassium carbonate. So now I have moles, I have volume, I can calculate for molarity. So we put it into the 200 milliliters, make sure you convert that to liters. Moles divided by my liters, and I get 0.0940 molar. As soon as we add this potassium carbonate into the solution, that is its concentration upon mixing. Now remember, this was the concentration of my K2 CO3, but there's only one CO3 in each of the compounds, so the molarity is the same. If somehow we had had CO3 2, then we'd be multiplying that molarity by 2. Always be conscious of what the compound is. If you're trying to use the concentration of the whole compound for the ion, make sure you keep into account how many of those ions are in each of the compounds. So, upon mixing, we can plug in their concentrations we've now solved for, 2.0 times 10 to the negative third, and 0.0940. We get a trial Ksp of 1.9 times 10 to the negative fourth. We compare my trial Ksp to the original Ksp. We get 6.8 times 10 to the negative 6 was the original. I found this on a given Ksp table. It could also have been given in the original problem. So my trial Ksp is greater than my Ksp, and therefore a precipitate does form. The last thing we're going to talk about is altering the solubility. These two concepts will be what is the common ion effect and how it can be used, and how we can increase or decrease the solubility of a compound by adding other materials. So the first thing we need to identify is Le Chatelier's principle and how that can apply here. So remember, Le Chatelier's principle states that when a stress is applied to a system at equilibrium, the equilibrium will shift so as to partially counteract the imposed stress. In solutions, this applies like this. By adding an ion to a pre-existing saturated solution that already contains that ion, the equilibrium will shift to return to the Ksp by forming a precipitate. In other words, if we always have our reaction, where we have reactants are in equilibrium with our products, and our solid is on this side, our precipitate. When we add a common ion, we're adding to the ion side, so we're adding over here. So add away, and we will shift to produce more of our solid, more of our precipitate. For example, if I have calcium carbonate in equilibrium with its ions, so we have a saturated solution of calcium carbonate, so we're going back and forth from the solid sample. So if we were to add a small amount of calcium chloride to this beaker, let's see what it would do. Well, first off, calcium chloride is considered to be soluble, so it's going to break apart into its ions. And one of these ions should affect the solution already. Well, that would be the calcium ion. So we're essentially just adding some calcium ions and some chlorine ions to the solution. The chlorine ions will be spectators, and the calcium ions will play an effect. So these are just spectators, but this calcium ion is going to increase the concentration of calcium ions in the solution. So according to Le Chatelier's principle, increasing the calcium concentration can be counteracted by the equilibrium shift to the left. We added here, therefore add away. We shift to the solid, we shift to the reactant side. What this will do is increase the amount of solid calcium carbonate. By increasing the amount of solid calcium carbonate, we're also decreasing the concentration of carbonate. Since this results in more calcium carbonate in the beaker, we can say that adding the calcium ions to the solution decreases the solubility of calcium carbonate, because we are actually shifting more towards the precipitate. We're less soluble of the precipitate. Soluble is the amount that this dissolves. Well, it's dissolving less if there's more of it now. So a compound of low solubility forms two ions in a saturated solution. The addition of either of these two ions from a compound or a solution with an ion in common will decrease the solubility of the compound originally, or the one that was considered to have a low solubility, whatever our solid was. So increasing solubility. We can use the Chatelier's principle for increasing the solubility of a compound, as well as for decreasing it. So let's look at this equilibrium again. Calcium carbonate breaking apart into calcium and carbonate ions. We can shift the equilibrium to the left in two ways. One, we can form a different precipitate with one of the two ions. If we did this, then this would be the take away. So if we take away a carbonate by forming some other compound, so XCO3, that would be take towards. We can also add an acid to the carbonate or a hydroxide. So this is a special case. We're going to look at this one next. So if I add an acid to carbonate specifically, HCl specifically, if I'm using this strong acid, it's breaking apart into its hydrogen and chlorine ions. My H ions, because I said any acid, it didn't matter which one, my H ions will react with carbonate to form H2CO3. And H2CO3 is a special compound. It doesn't actually stay as H2CO3 for long. In water solutions, carbonic acid is unstable and therefore it decomposes into carbon dioxide gas and liquid water. Now you should understand this because you usually drink things with this. Most beverages are carbonated using carbonic acid nowadays. Because this carbonic acid separates into water and carbon dioxide, they'll fill your drink, whichever one it needs to be carbonated, with carbonic acid and put it under high pressure so it stays in this liquid phase of carbonic acid. Then as soon as you open it and you hear that fizzing sound, you're actually allowing this to decompose into the two compounds it generally decomposes into, H2O and CO2. Notice this isn't one of our strong acids, so it doesn't fully dissociate, but it mostly dissociates. As a sidebar, this is also why we talk about how all of your carbonated beverages are very, very acidic, because it actually does leave some of this weak acid in that drink. So this carbon dioxide gas is going to escape from the solution, therefore it creates this continual process to the right. So this is why there is a special situation where if you add an acid to something with a carbonate, it will continually decompose that original solid because it is continually doing the take towards wherever the carbonate was. This is continually being used up by the acid, and so therefore we continually have a take towards reaction occurring. So as long as more acid is added, this process will continue until all of the solid, whatever solid had the carbonate in it, has been dissolved. So this is a specific case that only works whenever we have a carbonate or a hydroxide, because hydroxide will do the same thing. The hydroxide will continually bond with any of the added hydroniums from whatever acid you added, and will continually pull the reaction towards the right until you've used up all of the solid. So adding an acid to a low solubility compound that has a carbonate or a hydroxide in it will decrease the concentration of the carbonate or hydroxide and therefore increase the solubility of the compound. So we had our reactants, which was our solid. We had our products, which one of these was a CO3 or an OH minus. And because we were taking this away, we're doing take towards. And you continually move towards the product side using up the solid. We said the other way to increase solubility was by forming another precipitate. So if in the following equilibrium my silver ion concentration is decreased, the equilibrium will shift to the right, because we'll have a take away towards. So if I want to use up this silver, if I want to change its concentration, I can add something that will form a precipitate with the silver, therefore using up this silver and lowering its concentration. So it is found that if you add sulfide ions to this solution, the sulfur ions will form a precipitate with the silver. This process can be represented as follows. So I have solid silver chloride reacting. But when I added something, didn't matter what, that had some sulfide ions, this sulfide is going to pull away some of this silver to bond to form silver sulfide. So as this lowers this concentration here, then we have a take towards, which is using up the silver chloride, pushing it towards the product side. You would have to add a solution that would contain a soluble compound with that sulfide in order to have these free-floating sulfides. So sodium sulfide, potassium sulfide, ammonium sulfide. Those would be the three really good options for this. Another option for this same reaction is you could try to use up the chlorine instead. So chlorine forms a precipitate with lead. So if I add some sort of solution that has lead ions in it, then the lead ions will take away some of this chlorine. So we have a take towards occurring again, which would once again use up some of this solid silver chloride. Remember, in both cases, we can't just add lead ions. Nobody has just a solution of pure lead ions. You need to add something where that lead is attached to something else. So like a lead nitrate would be very good. So lead 2 nitrate in this case because it has a 2 charge.